Hello students, welcome you all to this lecture. Today we are going to discuss about the application of balanced Houston bridge. Okay, so the first application for the balanced Houston bridge condition is meter bridge. So what is meter bridge? So meter bridge is such an instrument which is used to determine the value of an unknown resistor. Okay, the resistance of an unknown resistor. To determine the value of that unknown resistance of a resistor, we used an instrument in a lab that is known as meter bridge, which is based upon the principle of what? Balanced Houston bridge condition. Okay, and as the name shows, it consists of a wire of length 1 meter. That's why it is known as a meter bridge. So the structure or construction of the meter bridge like this. There are two metallic strips of L shape, which are mounted on a wooden board. Okay, like this. Okay, these two are mounted on a wooden board. If this is the wooden board, the two metallic strips of L shape are mounted on this wooden board. Okay, and there is another metal strip which is placed here in such a way that it creates two gaps between these two metallic strips. Okay, and 1 meter length of a resistor wire, named it as A, B, is connected across these two metallic strips, and there is a meter scale which is mounted below this wire. Okay, and this is a meter scale which is mounted below this wire to measure okay. So this is a meter scale which is mounted below this wire, and this wire is made up of a alloy. Maybe it's a concentran or manganese. So this connecting wire, whose length is 1 meter, is made up of an alloy. So in between these two gaps, okay, between the right side, left side gap, we connect a resistance box. What is a resistance box? It is a box from which we can choose any resistance in a certain range according to our choice. Clear? And in the right side gap, the unknown resistor is connected, whose resistance we have to find. Okay, so in the left side gap, in between these two strips, a resistance box is connected, and the unknown resistance, whose resistance is to be determined by using the meter bridge, is connected across the right side gap between the straight and L-shaped metallic strip. Clear? And a cell is connected across the two terminals of the 1 meter wire length. Okay, through a key. Clear? And from this terminal, there is a galvanometer is connected through a jockey. Okay, clear? So this term is known as a jockey. Clear? So this is the diagram of a meter bridge, in which there is a connecting wire of length 1 meter. Clear? As this is the length of 1 meter, so I can write it here as 100 centimeter from B to A. The length of the complete wire, which is mounted over a meter scale, and there is two metallic L-shaped strips and a straight strip which create two gaps in between this, and at the left side gap we connect a resistance box from which we can choose any resistance within a range according to our choice, and from right side gap we connect the unknown resistance whose value we have to determine by using this meter bridge. Okay, so what is the process, how we have to determine the unknown resistance of this resistor by using the meter bridge. So we know this meter bridge is used on the basis of what? Balanced condition of Wheatstone bridge, and as here is a galvanometer is connected between this terminal with a jockey, so let this jockey can slide over this connecting wire from point A to point B. So just mark this point A as 0 and this point B as 100, the complete length of the connecting wire. Okay, so by heat and trial method, let at any point P, it's such a point, if we place the jockey at this point P, then the galvanometer shows zero deflection. Okay, so if by heat and trial method there is such a point P where the galvanometer shows zero deflection, that means what? There is no current is flowing through this galvanometer, and we know in a balanced Wheatstone bridge condition, if I am comparing this connection with a balanced Wheatstone bridge like this, let this resistor be the resistance box, and here is the middle terminal from which a galvanometer is connected with a jockey, and this resistance is the unknown resistance, and the length from A to this point P, let this length be L1, where the galvanometer shows what? Zero deflection. This point P, the point P is known as null point, where the galvanometer shows zero deflection. Okay, where the galvanometer shows zero deflection. Okay, so this is the point P known as null point where the galvanometer shows zero deflection. Okay, so this is the point where the galvanometer shows zero deflection. That means if this length is from this end 0 is L1, then the remaining length from P to B, this will be 100 minus L1. Clear? So comparing this with the balanced condition of Wheatstone bridge, if this resistor is the resistance box, this resistor is the unknown resistance, from this length to this length, this resistor has a resistance because the length varies, then the resistance will vary because for the complete length of the wire the cross sectional area remains same and the resistivity of the material remains same, and we know R equal to how much? Rho L by A. If A remain constant, rho remain constant, then resistance is directly proportional to length. So if it has certain length L1, then we can easily find out the resistance which is directly proportional to the length. So this will be the length L1. Clear? And from this point to this point will be the remaining resistance of the resistor, that is 100 minus L1 will be the remaining length. So let this will be 100 minus L1. Clear? And this is the connection across the battery. Clear? And as for this point P, there is no current flowing through this galvanometer, so the value of Ig will be 0. Then we can say that the complete Wheatstone bridge in balanced condition. So from this figure we can write the resistance of the resistance box that we choose divided by the resistance of the length L1 must be equal to the unknown resistance divided by the resistance of the length 100 minus L1. Clear? So from this implies you can find out, let the resistance box resistance be R ohm. Okay, the resistance of the resistance box for this particular condition be R ohm. So this will be R divided by L1 equal to unknown resistance UR divided by 100 minus L1. Simplifying this, we will get the unknown resistance will be equal to how much? 100 minus L1 into R divided by L1 ohm. Okay, so this is how we can find out the unknown resistance by using a meter bridge. Clear? So here the R is the resistance that we draw from the resistance box, L1 is the length of the null point or distance of the null point from the 0 end, and the remaining length is 100 minus L1. As we know, the length of the complete wire is 100 centimeter or 1 meter, that's why it is known as meter bridge. So this is how we can find out the value of a unknown resistance by using what? The meter bridge. Clear? All of you understand? So basically the meter bridge is based upon the principle of balanced condition of Wheatstone bridge, for which for a particular position of the jockey, when there is no deflection in the galvanometer, we can say that the ratio of this resistance by the length of this conducting resistor with the ratio of the unknown resistance by the resistance or length of the remaining resistor. And as the complete resistor is same, the cross sectional area remains same and the same current is flowing through it, then we can say that the resistance of the connecting resistor is directly proportional to what? Length of it. That's why we can replace the resistance by its length. Clear? Okay, the next application of Wheatstone bridges, that is a potentiometer. Okay, so potentiometer is a device which is used to measure the EMF of a cell without drawing any current from it. Okay, because we know voltmeter is also used to measure the potential difference, but by using the voltmeter it draws some current from the cell. But if we are using a potentiometer, it will draw zero current from the cell. So by using a potentiometer we can correctly measure the EMF of any given cell. Clear? So potentiometer is a device which is used to measure the EMF of a given cell. So what is a potentiometer? It is used to measure the EMF of a cell without drawing any current from it. Okay, so potentiometer is a device which is used to measure the EMF of a cell, without drawing any current from it. Okay, voltmeter is also used to measure the EMF or potential difference across the cell, but it draws some current. So that's why by using a potentiometer you can measure the EMF correctly. Okay, it is based upon the principle what? If for a given resistor, if this resistor is fixed, then its cross sectional area and resistivity remain constant. If the current flowing through the resistor is also remain constant, then the potential difference across this resistor will be how much? V can be written as I into R, or we can write this as V is equal to I into rho L by A in place of R. As we know, R is equal to how much? Rho L by A. So if the resistor remain fixed and current flowing through it remain constant, then you can say that V is some constant I rho by A into L. Because these all things remain constant, so we can write V equal to some constant lambda into L, or this implies you can write lambda is defined as V by L. What is lambda? Lambda is known as potential gradient. That means the potential across the resistor varies with respect to its length. Clear? If the current and the resistor remain fixed, then the potential across the resistor will change directly with its length, defined as potential gradient. Clear? So how to determine the EMF of a cell by using a potentiometer? So basically the potentiometer is quite similar to that of a meter bridge, but a little bit difference with its construction. So what is the potentiometer actually? So potentiometer is consists of a large connecting wire as that of a meter bridge. In meter bridge we used a wire of length 1 meter, but in potentiometer we used a wire generally of 4 meter or 10 meter. Okay, so if I am constructing the wire is connected across a board, if this is a board, then the total 4 meter or 10 meter wire is connected along the two strips in this zigzag manner. Okay, like this. Clear? And there is two ends, A and B, and a battery is connected across these two terminals. Okay, this is basically, and the complete system is mounted over a wooden board. Clear? So I am just drawing the circuit diagram for the potentiometer only. So I am just drawing the complete length of the wire, that is named as AB. Okay, and the length of this complete wire is 4 meter. So potentiometer is basically have two circuit diagrams. One is primary circuit. This one is the primary circuit, in which there is a battery connected through a rheostat and an ammeter and through a key K1. Okay, this is a rheostat and this is a battery having potential V. Okay, this circuit is known as the primary circuit of a potentiometer. Okay, so in primary circuit, a battery, a rheostat and a ammeter is connected across the wire of the potentiometer through a key K1. Okay, so if I am closing this key, then there is a current flowing through this wire AB. Then we can find out the potential difference across the wire AB as I into resistance of the wire AB. Clear? Because the current I is flowing through this across this wire and the resistance of the wire is RAB, so we can find out the potential difference VAB equal to I into RAB. So this implies we can write VAB equal, what is the value of I? If this is the potential V, let it be denoted by E. If this is E, then current will be E divided by the RAB plus the rheostat potential. It is a variable potential, but for any instant we can make this as a constant resistance. So it will be RAB plus RH into RAB. Clear? This is the total current which is remain constant for a given situation, because the length of the wire remain constant, the resistance so remain constant, the resistivity of this wire remain constant. That's why the complete resistance of the potentiometer wire remain constant, and for any given condition the resistance of the rheostat is also remain constant. So current flowing through the circuit is remain constant. So we can find out this total I is constant. So this implies we can find out the VAB is equal to some constant lambda into length of wire AB, because we can find out RAB is equal to rho into LAB divided by cross sectional area of the wire. So these all remain constant. So potential difference across the wire AB is directly proportional to the length of the wire AB. So from this we can find out the potential gradient lambda is equal to how much? The potential difference across the wire AB divided by length. Clear? You have to remember this. This is what the potential per unit length of the wire. If we are marking the point A as 0 and the complete length B as L, then this is the potential difference across the wire AB per unit length, or which can be defined as what? Potential gradient. We all know about this. Okay, so now how to find out the EMF of a cell by using this potentiometer. So if across this circuit, now this is the secondary circuit for potentiometer, I am connecting a cell, let it has EMF E1, okay, through a galvanometer which is connected through a jockey J. Okay, clear? Now I am connecting this jockey at this point, let P, by heat and trial method. Okay, so this jockey can be vary along the length of this wire AB. So by heat and trial method, I got a point P where the galvanometer shows zero deflection. That means what? If at this point P, let the distance from A, the zero side, the length is L1 for point P. Okay, I am getting this point P by heat and trial method because I can vary this jockey from 0 to L length, okay, randomly, and I got such a point P where the galvanometer shows zero deflection. What does it mean? If the galvanometer shows zero deflection, that means there is no current flowing through this galvanometer. Okay, if the galvanometer has no current flowing through this, that means it shows zero deflection. That means the potential of this cell must be equal to the potential of the length of this resistor. Clear? Because we know current flows from higher potential to lower potential always. So if for this point P or for this length L1 there is no current flowing through the galvanometer as it shows zero deflection, that means there will be no potential difference. That means the potential of the length AP or L1 must be equal to the potential across the battery, that is E1. If the length L1 has less potential in comparison to E1, then there must be a current flowing from the battery through the circuit like this. If the potential of the L1 is more than that of E1, then there will be a current flowing through the circuit like this. Clear? All of you understand? Just understand, if the potential of the length L1 is more than that of E1, then current will flow from higher potential to lower potential like clockwise, anti-clockwise cells. Clear? But if the cell has more potential in comparison to the length L1, then current will flow from higher potential to lower potential through the circuit like this in clockwise sense. But as there is no current flowing through the galvanometer because it shows zero deflection, that means what? The potential difference of this cell must be equal to the potential of this length L1, and we know the potential per unit length of the wire AB, lambda, is defined as what? V by L. So the potential for the length L1, that is potential difference across the length L1, will be how much? Lambda into length L1. Clear? So this will be the potential difference across the length AP, that is VL1 is equal to lambda into L1. Let it be equation 1. And the EMF or the potential difference across these two terminals of the cell is E1. So we can write E1 must be equal to VL1 as there is no current, as galvanometer shows zero deflection. So from this we get the E1 is equal to how much? Lambda into L1. Okay, so this is the value of what? EMF of this cell, which is equal to lambda into L1, and we can easily find out the value of lambda. We already discussed previously that the value of lambda will be how much? V by L. And what is V? V equal to I into R, complete resistance of the potentiometer wire. Clear? So this is how we can find out the EMF of a cell by using a potentiometer. Now we have to use the potentiometer to compare the EMF of two given cells. Okay, so how to use the potentiometer to compare? The first use of potentiometer is to compare the EMF of two given cells. EMF of two given cells. Okay, so for this we have to connect two cells across this potentiometer. So from this connection I am connecting two cells like this. Let it be E1 and this is E2, and the negative terminal of these two cells are connected across the two terminals of a two-way key, and from the middle terminal the galvanometer is connected. What is two-way key? That means you can use this key along two sides. Okay, let naming this as X and Y are the two terminals, and O be the middle terminal of the key. So once we can use OX as a key, then we also can use OY as a key. Okay, so let for the first condition I am closing the key along this side. Okay, so now the OX side is closed, so the cell E1 is active in this circuit. Okay, E2 is not active because as the OY side is open. So for the first condition I am closing the OX side, that's why throughout the circuit the cell E1 is in connection. Okay, so similarly for as the before case, I am moving or dragging this jockey throughout the complete length AB, and for a particular point P I am getting the length L1, for which the galvanometer shows 0 deflection. That means for this length L1 the potential difference across the cell E1, that is the EMF of the cell E1, must be equal to the potential of the length AP. So previously we already derived, so from here we can find out the, if when I am closing the key along OX side, E1 is in connection with the circuit, I am getting a point P where the galvanometer shows 0 deflection. So let for case 1, when E1 in use, okay, case 1 when E1 in use, let P be the null point when galvanometer zero deflection. So this implies you can write the EMF of the cell E1 must be equal to the potential across the length L1. So you can write that is lambda into L1. Okay. What is lambda? Lambda is the potential gradient, that is potential per unit length. So for the L1 length the potential will be lambda L1, let it be equation 1, which is equal to the EMF of the cell E1. Clear? As we already derived before. Now for case 2. Okay, in case 2, if I am opening this side, okay, now I am closing the side OY. So now the cell E2 is in connection. Okay, so case 2 when E2 is in use, when E2 is in use, so when we are using E2 by closing the side OY, so in the circuit now E1 is inactive and E2 is active. So by hit and trial method I am getting another point Q. By joining the jockey at point Q, I am getting 0 deflection in the galvanometer. Let the distance from the 0 end be L2. Okay, so for E2 I am getting a null point at point Q where the galvanometer shows 0 deflection, and the distance point Q from the 0 end, that is from A end, is L2. So if at point Q the galvanometer shows 0 deflection, then we can find out E2 must be equal to lambda into L2, because as the galvanometer shows 0 deflection at point Q for the cell E2, that means the potential of the E2 cell is equal to the length of AQ, that is L2. So we can find out the total potential of the length L2, that is lambda into L2, because lambda is the potential per unit length across the potentiometer wire AB. So this will be the EMF of the cell E2. Now we can easily compare from equation 1 and 2. We get E1 by E2 equal to lambda L1 by lambda L2. This implies we find out E1 by E2 equal to L1 by L2. Okay, so this is how we can find out the EMF of two given cells, or we can compare the EMF of two given cells by using a potentiometer. Clear? All of you understand? So by measuring the length of the null point, we can easily find out the potential comparison or EMF comparison of two given cells. Okay, this is one application or one use of the potentiometer. Okay, there is another use also, that is how to determine the internal resistance of a given cell. Okay, the next use for the potentiometer is to determine the internal resistance of a given cell, and you have to remember that in the potentiometer application the primary circuit always remain fixed, so we have to only change the secondary circuit to determine what? The internal resistance of a given cell. So now the second application, determine internal resistance of a cell. Okay, so now here I am connecting a cell with some internal resistance. Let the EMF of the cell is E and there is internal resistance small r. Okay, and this circuit is now connected across a external load resistance capital R through a key K2. Okay, and this end is connected through a one-way key through a galvanometer and a jockey. Okay, the connection is like this. This is the complete cell. Okay, this is the connection of a potentiometer to determine the internal resistance small r of the cell E. Okay, so now how we can find out the internal resistance small r for the given cell? So let or we can replace it like this. This is connected with a jockey like this. Okay, so when first of all, let case 1, the key K2 is open. Okay, when the key K2 is open, that means this key is not closed, it is open. That means there is this resistor R or external load resistance R is not in use in this circuit. So when the key K2 is open and I am randomly sliding the jockey over the potentiometer wire for which I am getting a point, let it be the point here P, for which the galvanometer shows zero deflection. Okay, remember for the first case, when the key K2 is open, that means there is no current flowing through this circuit. I am getting a point P where the galvanometer shows zero deflection, and let the distance from the zero end be L1. Okay, so case 1, when the key K2 is open, let P be the null point when the galvanometer shows zero deflection. This implies the EMF of the cell E must be equal to lambda into L1. Why? Because what is the definition of EMF? EMF is the potential difference across the two terminals of the cell when there is no current drawn from the cell, and as this key K2 is open, there is no current is drawing from the cell, and as the galvanometer shows zero deflection, so the potential difference of the length L1 must be equal to the potential difference of the cell, and there is no current drawn from the cells, which means the potential difference of the cell is equal to its EMF. So we can find out the EMF of the cell must be equal to lambda L1. This is from the first case, let it be equation 1. Okay, now case 2, when K2 is closed. Okay, when the key K2 is closed. Now as the key K2 is closed, certain current I will flow through this external load resistance R, because as this current get closed, some current is drawn from this cell along the load resistance R. Now I am again sliding the jockey by closing this key K2 over the potentiometer wire, for which I am getting another point, let it be here Q. Okay, when the jockey is at this point Q, the galvanometer shows 0 deflection. Let the length be L2. Okay, so case when K2 is closed, some current is drawn from the cell. Okay, when the K2 is closed, some current is drawn from the cell, and during this, let Q be the null point. Okay, and during this, let Q be the null point when the galvanometer shows 0 deflection. Q be the null point when the galvanometer shows 0 deflection. That means here we are measuring what? The terminal potential difference of the cell, because if at point Q the galvanometer shows 0 deflection, that means the length of the AQ or L2 potential difference across the length L2 must be equal to the potential difference across the cell's terminal, and as here the current is drawn from the cell, so the terminal potential difference will be the potential difference across the cell. So in second case, we can write so from case 2, we can get the terminal potential difference V of the cell is equal to how much? Lambda into L2. Let it be equation 2. Okay, as during the second condition the key K2 is closed, so some current is flowing through this circuit, and Q is the null point at which the galvanometer shows 0 deflection. That means the potential difference of the length L2 must be equal to the potential difference across the two terminals of the cell, and as certain current is drawing from the cell, so the terminal potential difference is V. So V can be defined as lambda L2, and we know the internal resistance R is equal to E by V minus 1 into R. What is R? R is the load resistance, and from equation 1 we get the EMF of the cell, from equation 2 we get the terminal potential difference of the cell, and we know the external load resistance R because we are considering this R. So from this we will get the internal resistance, let it be equation 3. So by using 1 and 2 in 3, we get the internal resistance small r is equal to lambda L1 divided by lambda L2 minus 1 whole into R, and by simplifying we will get what? The value of the internal resistance of the given cell. This will be how much? R equal to L1 by L2 minus 1 whole into R, or this implies R equal to L1 minus L2 divided by L2 whole into R. So this is the expression for the internal resistance of the given cell. Okay, so this is the two application of a potentiometer by using which we can determine or comparing the EMF of two given cells, and as well as we can also determine the internal resistance of the given cell. Clear? This is most important. You have to remember all the formulas to find out the potential difference of a cell, or to compare how to compare the EMF of two given cells, or how we can find out the internal resistance of a cell. Clear? So this is all about the application of Wheatstone bridge in case of meter bridge and potentiometer. Okay, clear? So if you have any doubt, you can ask. Thank you.